Section 11.5 is lines and planes in space. So we're going to start with lines. So consider a line in space. Let's draw it like this. That goes through some point P. Let's call it x1, y1, z1, and is in the direction of some vector, so parallel to some vector v, and let's call that ABC. Okay, so the line L through P and parallel to V. Well, it consists of all points Q such that, ST for such that the vector PQ is parallel to vector V. All right, so think about a point Q is on this line if and only if that vector PQ is parallel to V. All right, well, what does it mean for two vectors to be parallel? We talked about that in class last time. That means that vector PQ is a scalar multiple of V. So it looks like TV, where T is a constant. And in particular, that means that vector PQ looks like x minus x1, y minus y1, z minus z1, where x, y, z is point Q. And that's going to be equal to T times the vector ABC. That's my V, right? And this is exactly what gives us our equation of a line. So we're going to look at two formulations of the equation of a line. The first is parametric equations. So if you remember from Calc 2, parametric equations, we just give a formula for x in terms of t and a formula for y in terms of t. And now that we're in Calc 3, we also need a formula for z in terms of t. So the line L parallel to V and through point P has equations. X is equal to x1 plus AT. Y is equal to y1 plus, BT, sorry. I have an eraser. Let's use it. And Z is equal to Z1 plus CT, where again, X1, Y1, Z1 are the coordinates of point P, and ABC are the coordinates of vector, or the components of vector V. Okay. We can also express the equation of this line using a symmetric equation. So as long as A, B, C are not 0, I can take these equations up here and solve them all for t and then set them equal. And that's exactly what we do to get our symmetric equations. So I get x minus x1 divided by A equals y minus y1 divided by B equals z minus z1 divided by C. Okay. All right, so let's look at some examples. So the first one I want to do is find both equations of the line through the point P, which is 214, and parallel to the vector V equal to 5, -2, 3. Okay. So V gives us our direction. And in fact, it's called the direction vector. Oops, vector. Think about when we do the equation of a line in 2 space, what we need is a point and a slope, right? So V is like our analog to the slope in 2 space. All right, and we just plug into the formula. So here is my x1, y1, z1, and here are my a, b, c. So my parametric equations, I just do x equals x1, so 2 plus a, 5t, y equals 1 minus 2t, and z equals 4 plus 3t. If I want to get the symmetric equation, I just solve for t in each of the equations above and set them equal. So I get x minus 2 divided by 5 is equal to y minus 1 divided by -2 is equal to z minus 4 divided by 3. And that's it. Let me make a comment here. I'm out of space, but I want to keep these. So I'm going to copy this and glue it on the next page for a second. Okay, so let's note, these equations aren't unique. So for example, if say t is 1, I'd get the point Q. So think about what happens when I plug 1 in for t up here. Q is going to have the coordinates 2 plus 5, so 7. 1 minus 2 is -1, and 4 plus 3 is 7. And this is a point on the line L. And if I used Q instead of P, to get parametric equations for the line, we'd get x equals 7 plus 5t, y equals -1 minus 2t, and z equals 7 plus 3t. Is also a set of parametric equations that traces out this line. Now there's nothing wrong with that, right? These are both going to give us the same line. All this does is shift what happens at different values of t. So here, to get the point P, we want to plug in t equal to -1, right? All right, I want to show you how to graph this in GeoGebra real quick. So let's switch to GeoGebra. Now, when you're graphing parametric equations, you're going to type curve, so C-U-R-V-E. And you can see here it shows you what you need. So if you're doing a curve in 2 space, you just need an expression for x, an expression for y, your parameter variable, and then your start and end value for t. And in 3 space, you'll need 3 expressions. Okay, so I'm going to do parentheses. And let's go here. So what was our line? 2 plus 5t. And then I had 1 minus 2t. Oops. And then I had 4 plus 3t, right? Then we say our variable is t, and let's just go from negative 50 to 50. And there you see, here's our line. Okay. And we can double check that that line goes through our point. What was our point here? It was 214. And there you can see my point. Oh, I typed the wrong thing. 214. There we go. Now it's on the line. All right. Okay. Let's try one more example. Let's find parametric equations for the line through the points. A is 2, 4, negative 3, and B is 3, negative 1, 1. Now this is just like when in 2-space you're given 2 points and asked to find the equation of a line. You had to find the slope, right? So here, instead of finding the slope, you're finding the direction vector. So how do I determine a direction vector? Well, the line has to go through A and B, so it has to be parallel to the vector that goes from A to B, or vice versa, from B to A. Okay, so let's find vector AB. So remember, to find that vector, I'm going to take the coordinates of B and subtract the coordinates of A. So I get 3 minus 2, and negative 1 minus 4, and 1 minus negative 3. So that's the vector 1, negative 5, 4. And then just pick a point. You can use A or B. I'm going to use A. So the line has parametric equations. X equals 2 plus 1 times t, y equals 4 minus 5t, and z equals negative 3 plus 4t. And you should be able to give a rough sketch of this line by hand. You can also check, whoops, that's not z. You can also check in GeoGebra. So my points are 2, 4, negative 3. So 1, 2, then 1, 2, 3, 4, and then down 3. 1, 2, 3. So say here's A, and B is 3, negative 1, 1. So 3, negative 1, and up 1. It's about there. And I don't have a straight edge, so as close as I can. Here's my line now. All right.